Okay, this is number 2 of the binary videos, and we're going to again review kind of how to count in binary, and then we're going to get into a little more of how to go from decimal to binary and binary to decimal, and provide a little bit of refresher off of the first lesson. Now again, what I'd like you to do is to go ahead and write out your number line. And go ahead and write the first 10 numbers in binary. In decimal, that'd be 0 through 10. Just write the first 10 binary number sequences in order down. So go ahead and do that, and then you can check it against my work here. Okay, this is what you should have come up with. You should have come up with 0, 0, 0, 0, 0, 0, 0, 0, 0 for equivalent of decimal 0. For 1, we should have incremented that bit because it was available, the first bit, and zeros for the rest. For binary 2, because the first bit was full, we'll set it back to 0, increment the next bit, then the rest, of course, are zeros. That gives you a binary 2. For the next one, the first bit is available, so we'll increment that, leaving the rest alone. And that equals 3, and that equals 3 on the number line as well. This bit is full, so we'll set it back to 0. The second bit is full, we'll set it back to 0. We'll increment the third. And again, that'll form a binary, or 4 in decimal, and that matches the number line as well. For binary 5, well, thought I cleared my board. Let me try again. For binary 5, as you can see off the number line at the top, that will be the equivalent of a binary 5. For 6, this first bit is full. We'll set it back to 0. We'll increment the second bit. We'll leave the others alone. And on the number line and just via counting, that'll equal 6. The first bit is empty. We can increment it. We'll leave the rest alone. That forms a 7. As you can see, we would just continue on for the next numbers. You should start seeing the patterns develop by now. If not, go back and review these videos until you can see the patterns developed. All right, now you go ahead and do the numbers 10 through 17, see how you do, and then you can compare them to my answers. Okay, a 10. Zeros out here. A 1 in the 8 column. A 1 in the 2 column, and that'll give you 10, right? Or if you want to keep counting up instead of using the number line, this one is the first bit has available space, so the next one will be 1. We'll leave this one alone. That gives you 11, and looking up the number line, 8 plus 2 plus 1 is 11. For 12, this bit is full, this bit is full, so we'll set them to 0. We'll increment the first available bit, leaving the rest alone. We get 12. Incrementing the first available bit is 1 here, leaving the rest alone then. Once we increment the first available bit, we leave the rest alone. And we can also look at the number line. 8 plus 4 plus 1 is 13. And perhaps most of you will find that's probably the simpler way. To get 14, the first position is full, so we'll set it back to 0. We'll increment the bit 2, leaving the rest alone, and we end up with 14. We increment the first position because it's available, leaving the rest alone. Looking up at the number line, that makes 15, and it makes sense since that's the next increment. For 17, let's use the number line method. A 1 in the 16 and a 1 for 1, right? Everything else would be zeros, and that gets you a binary 17. Alright, now that's an easy way of doing it with the number line, right? One way is counting. We could count all the way up to 17, or we could just use the number line to get 17. Obviously, the number line is very simple. So once you have that number line written up at the top for 8-bit binary numbers, it's not going to change. So if I wanted you to find, let's say, 32, well, that would be one you could just look at and tell what it is, right? You could put a 1 in the 32 and a 0 everywhere else, and that would get you 32, right? If I told you to find 50, you might also could just look up there and tell that one. 32 plus 16 is 48, plus 2 would be 50. And perhaps you could even do that. Most folks probably could not, or not familiar enough with binary to do that. The universal method is if I told you to find 113, how would you do it? Well, looking at the number line, you try the biggest number first. Can you take 113 and subtract 128 and get a positive number? Well, the answer is no. So because of that, we'll put a 0. Can you subtract 64 from 113? Well, the answer is yes. What's left over? Can you put 32 into 49? Yes. 49 minus 32 is 17 remaining. Can you put 16 into 17? Yes. So we put a 1 in the 16 column. We have a remainder of 1. The remainder of 1 will go in the ones column. And now you have 64 plus 32 is 96. Plus 16 makes 112. Plus 1 makes 113. And that's how you can get 113 from decimal to binary or vice versa really quick. Okay, let's try another. So again, the magic number line here is your friend. If you're going to be a digital engineer, you would need to be able to do this without the number line. And 128. Once you get this number line down, it gets to be really simple doing the binary problems. Like I said, if you're a digital engineer, you'd have to do more than this, but that's not what we're worried about. We're just trying to do binary numbers so we can do IP addressing. So that's about it. All right. Let's do a few binary to decimal problems. Let's say I gave you the binary number 10100011. What would it be in decimal? It's a very easy problem. All you simply do is look up at the number line, make sure the numbers are lined up. You have a 1 at the 128, so you add that. You have a 0 in 64, so you don't add anything there. You have a 1 in the 32 column. You have a 1 in the 2 column. And you have a 1 in the 1 column. There's your answer. It's just simple addition. It's really not that difficult to do. Okay, let's try another. Let's say I gave you 10101010. What is the binary equivalent? I mean the decimal equivalent. And these are separate problems, obviously. I'm not saying that this binary number follows the one above. We're not counting here. We're simply solving problems. How would you convert this binary number to decimal? Well, you'd have 128. 64 is a 0, so we'd add 32 plus 8 plus 2, right? And that would be 170. Let's do another. Suppose I gave you 111000. Well, that would be 128 plus 64 plus 32 plus 16, and that is the answer, 240. So as you can see, converting binary numbers to decimal numbers when they're all 8-bit numbers are very simple. It's not a difficult problem. All right, let me try to give you some decimal numbers and have you convert those to binary. Let's write our number line again. And I want you to find the number 205 in decimal. We'll start out the 128 column. 205 minus 128. Will 128 fit? Yes. $77. Will 64 fit? Yes. Will 32 fit? No. Will 16 fit? No. Will 8 fit? Yes. Will 4 fit? Yes. Will 2? No. Will 1? 1 minus 1? Yes. 1100 1101 is 205. Give you one more here. 196. $16 minus 8 is 8. 8 minus 2 is 6. So we can put a 1 out here. Will 64 fit? Yes. 32, no. 16, no. 8, no. 4, yep. And that will leave nothing left. So that is the equivalent of 196 and binary. Let's do one more binary to decimal. If I gave you the binary number 0, 1, 1, 0, 0, 1, 1, 1, how do I get it to decimal? Again, I simply add up the values under the number line. And get 103. All right, that's the second problem on binary, and that is conversions with 8-bit numbers from decimal to binary and binary to decimal. It's really not a complicated process. There are some exercises I'm going to have you do shortly here. Make sure you finish the PowerPoint presentation and any other videos you see in the online course area or that are referenced by the PowerPoint presentation. Make sure you watch all those. And if you have any difficulty, go back through these presentations and view them again or contact your instructor.